So in this short clip on rotational motion, we're going to look at introducing three concepts: angular displacement theta, angular velocity omega, and angular acceleration alpha. The first concept we're going to look at is angular displacement theta. This is measured in radians. Now we need to define radian. It's the ratio between the distance around the curve of the arc and its radius. So we generally write our angular displacement theta as equal to S over R. Now the special case is when S equals one complete circle. That's when we have, of course, the circumference C equals 2 pi r. That would be our special case, when S equals 2 pi r. So if we plug in that value for S in this equation, you can see the r's will cancel out, leaving us with 2 pi. And that is, of course, the angular displacement theta for one circle, 2 pi radians. So that means 360 degrees is the same as 2 pi radians. The radian itself doesn't actually have a dimension. It's not a proper unit. It's simply a ratio of two lengths, and that's why there's no actual dimension to the unit radian. So keep that in mind. It's simply a ratio. Here's an example. A spacecraft in a circular orbit completes exactly 115 orbits, and so what would be its angular displacement? Well, we can use this same equation we've just seen before. The missing thing in the box here, of course, would be theta. So that's theta equal to 115 times 2 pi, okay, because that's 115 revolutions, and each revolution is 2 pi radians, so we get a total of 722.6 radians. Now we could convert that into degrees simply by multiplying it by the ratio 360 over 2 pi, and that will give us you should get 41,400 degrees. Okay, the next idea we're going to consider is angular velocity, and the symbol is omega, which is a Greek letter. This is this lowercase omega. The big one looks like the symbol for the unit ohm. So of course this is purely circular velocity or curved velocity going around a point, whereas linear velocity has a symbol v. We're talking about straight line velocities only. This angular velocity is only considering circular paths where there's a certain speed or angular velocity. So it's useful for considering objects spinning in circles, things like records, discs, and merry-go-rounds, for example. Now comparing the definition for angular velocity, you can see it's similar to linear velocity v, which is defined as displacement over time, and in symbol terms is v equals d upon t. For a rotating system, the angular velocity is measured in radians per second, and that's equal to the angular displacement theta divided by time, again in seconds, and giving us the formula as follows. Okay, so here's an example looking at angular velocity. A propeller rotates at 600 revolutions per minute. What is its angular velocity? Well, we need to think about the angular displacement first. Theta, so this is the idea. We have 600 revolutions in each minute, so we need to multiply the 600 by 2 pi, which is the missing thing here. That tells us the number of radians each minute. In this case, 3,770 radians every minute, or 60 seconds. So now we are in a position to use the equation omega equals theta angular displacement over time. Plug in the numbers 3770 divided by 60, and you get 62.8 radians per second, often written in shorthand as rads or rad per second. Another useful relationship is to define an equation that relates the linear velocity v and to the angular velocity omega. If you consider a point moving in a circle, the instantaneous linear velocity v at a moment in time is defined as v equals the radius r times omega. Another useful equation. Here's an example. If the propeller we just saw before rotating at the same rate, 600 revolutions per minute, the question could be, given the radius 1.5 meters, how fast is the tip of the blade moving through the air? In other words, if you looked at one moment in time, what would its velocity be? So here, to do this, you need, of course, to find the angular velocity. And once you have the angular velocity, you can then plug it into this equation here and find the tip velocity. In this case, 1.5 times 62.8 gives you 94.3 meters per second. And if you multiply that by 3.6, you can find the speed in kilometers per hour, which is an impressive 339 kilometers per hour. This little note here is an important thing to understand. If you look at the radius and you make it smaller, if you go closer to the center of the axis of rotation, the linear velocity will decrease. We're saying it the opposite way around. The tip of the blade is the fastest moving part of the blade, whereas the angular velocity is constant for every part of the blade. Okay, and the last concept we're going to look at is angular acceleration, and the symbol is alpha. So this is only to do with acceleration around a circular path. Now, to define it, it's a bit like the linear acceleration, where we have the change of velocity over time. So inside this square should be a delta symbol, and likewise to define angular acceleration is the change of angular velocity over time. And the units are radians per second squared, because we're dividing radians per second by seconds again. Okay, so another way of thinking about change of angular velocity, of course, which is written as delta omega, is to consider that it's equivalent to the final angular velocity omega f minus omega I. And so we can write the equation for alpha, the angular acceleration, as the final angular velocity take away the initial angular velocity over time. An example. A spin drive starts at rest. That of course means that the omega I equals 0, starting at rest. So, and it rotates and takes 3 seconds to reach 60 revolutions per minute, which is equivalent to 6.28 radians per second. So that's our final angular velocity, 6.28 radians per second. So over here we can write down our change of angular velocity as omega f minus omega I, 6.28 minus 0, which of course is the same as the final angular velocity. So we can plug that into the equation alpha equals delta omega over t, and divide that 6.28 by 3, we get 2.09 radians per second squared. Now, angular acceleration is also related to the linear acceleration by a very similar equation to the one we've seen before. It's simply the radius times the angular acceleration. Very useful equation. Here's an example using that one. An ant is standing on a vinyl disc at a distance of 100 millimeters from the center. If the disc is accelerating, at 3.0 radians per second, what is the linear acceleration experienced by the ant? So we simply plug in the equation A equals R times alpha, 0.1, which is 100 millimeters change into meters, times the 3 radians per second squared. And that gives us 0.3 meters per second squared, the linear acceleration instantaneously at every moment in time. That would of course be applied to this towards the center of the circle in this case.